Good morning. My name is Thomas Tucker. I'm an engineer within my organization's IP NOC, and this is going to be a continuation of the video we produced last time, which was configuring the hardware as well as the system name for our Nokia routers. Well, this time we're going to get into configuring our physical ports and logical router interfaces. So we'll just take a quick overview of the physical versus the logical. Our ports are going to be our physical network interfaces. These are going to take the format module/adapter/port, and it's going to contain all of our data link attributes, our MAC address, our operating MTU, our port mode, whether it's a network port, access port, or hybrid, as well as our encapsulation. And next is our logical router interfaces. And again, these are going to be our logical network interfaces. It's going to take the format chosen by the operator, but it must begin with a letter. And it contains all of our network layer attributes. Our IP address, we can apply QoS. We can specify whether or not this logical router interface is a loopback interface. It'll also contain our physical port binding, and we always specify the logical router interface within any protocols that we wish to configure. And last but not least, router interfaces that carry traffic must be bound to a physical port. So there are certain circumstances where, for the sake of quote unquote tricking a certain type of service into remaining operup, you can bind a logical router interface to that service. So as long as the service sees that logical router interface operationally up, the service itself will remain operationally up. But again, in that example, that logical router interface isn't carrying any traffic. It's just there for the sake of fooling, for lack of a better word, that particular service. And here's what our physical and logical network, or our topology, is going to look like. Each service router has its own individual table that contains the logical router interfaces, those logical or IP addresses, as well as the physical port binding for that logical router interface. So for example, on N1, our system address, which is synonymous with a loopback 0 interface or a LO0.0 for Juniper interface, we're going to address that 1.1.1.1/32, and we're going to rinse and repeat that for all of our service routers. So N6, its system address is going to be 6.6.6.6/32. And this is just to be able to easily identify these service routers, as well as easily establish any type of peerings within a particular protocol that we might need to establish. And we'll look at our logical router interfaces with our physical port bindings. On N1, we see that the physical port module 1/adapter 1/port 1 is going to be bound to the logical router interface 2N2, and its logical address is going to be 10.1.2.1/28. Likewise, on N2, we're going to have a logical router interface called 2N1 right here. And its physical port is going to be module 1/adapter 1/port 1, and it's going to have the address 10.1.2.2/28. And same for the logical router interface 2N3. It's going to have the logical IP address 10.2.3.2/28, and it's going to be bound to the physical port 112. And of course, our system or loopback address for N2 is going to be 2.2.2.2/32. And we're going to rinse and repeat that for all of the service routers in our topology. What I'm going to do now is I'm just going to go ahead and start these routers and begin a console session into them. All right, so I'll take a second while these routers boot up. All right, so we're back at our login prompt now. And if you're following in the previous videos, we're going to make use of the commands window just to send commands to all of our active sessions so that we don't have to do so much repetitive behavior. So again, within Secure CRT, I've enabled the commands window, and I've instructed the commands window to send these commands to all sessions. So if I type admin admin in the commands window, it has logged me into each of our SRs. So let's just take a look at the config where we left off last time. You see that our system name is configured as N1, and we have all of our hardware configured. So our focus today is going to be on the port configuration. So this entire section right here, as well as the logical router interface configuration, but we'll get to that in a bit. So let's move back to our topology here, and let's take a look at our goals. So our goals are to configure physical ports module 1, adapter 1, ports 1 through 4, as network ports with an MTU of 9212. So the way we do that is first we enter the configure context, and I'll do this the old-fashioned way on N1 just for the sake of example. And we enter port 111's context. If I press tab here, you can see all the different options you have. You have your APS options, SONET, network, etc. And of course, with a question mark, you can see your options and each definition. So since MTU is a Ethernet property, we're going to head into the Ethernet context. Again, we can see all of our options, some provider backbone bridging in there. But this is where we specify our MTU of 9212 within our ports Ethernet context. So if we look at the information, we can say that within the Ethernet context, we've configured an MTU of 9212. And that's all we've done within the entire ports configuration context. By default, each port on the service router is going to be a network port. So anytime we have an access port or a network face or customer facing port, such as a service access point, we're going to have to specify that this port is an access port. It's no longer a network port. But by default, all the ports on a service router are going to have a pretty high MTU, and they're going to be configured as network ports. So we see we've got our MTU configured for port 1 in module 1, adapter 1, but it's still in an administratively down state. And that's because under our ports configuration, it is shut down. So if we enter the command no shutdown and look at our ports configuration, we see that we've configured an Ethernet MTU of 9212, and we've instructed the port to not be shut down. So I'll issue the command show port 1, and this shows me all the ports on module 1. I could zero down further and say show port 1//1. This will show me all the ports on module 1, adapter 1. So again, show me all the ports on module 1, adapter 1. Show me all the ports on module 1. Since these virtual SRs aren't extremely dense, we aren't dealing with a 12-slot service router with, paired MDAs per slot. We can get away with just the show port 1. As you can see, once again, our port 111's configuration is to have an Ethernet MTU of 9212 and to be no shut, which it is. So we'll just go ahead and knock the rest of the ports out. Port 112. Ethernet, MTU 9212, no shutdown. This is port 112's configuration. So we entered the port's context, entered its Ethernet context, set the MTU, went back to the port's context, and issued a no shutdown. So if we do show port module 1, you can see that 112 is configured correctly also. So I'm just going to do these other two in the same fashion. Port 113, Ethernet MTU 9212, no shutdown, good to go. And we'll do port 114. And just for the sake of example, you don't have to go into each context. So I don't have to go into the Ethernet context if I'm already in the ports configuration. I could just simply specify Ethernet MTU 9212. No shutdown. And again, it accomplished the same as though I took the extra steps of going into the Ethernet context, configuring the MTU, then going back into the ports root context. So show port module 1. You can see so far we've got ports 1 through 4 configured with our correct MTU, as well as all of them being in an administratively up state. So configure physical port 115 on N1 and N6 as an access port with .1Q encapsulation. So this is going to be our customer-facing interface, or our service access point, or our SAP. And the way that SROS handles a SAP is the same way that any switch would handle a switch port. So let's just go into port 115's configuration. So this is what it looks like by default. All right. It's in a shutdown status. It is a network port with an MTU of 8936. But we want to convert this into a switch port that'll accept VLAN encapsulated frames, because this is going to be the port that's actually facing our customers. So this is going to be where the customers interconnect with the service provider. So whenever you make changes to physical ports in SROS, the port must be shut down. And just for the sake of example, I'm going to issue a no shut on 115. And what we're going to be dealing with is the encapsulation type as well as the ports mode. Both of those options are found within the Ethernet context. So as you can see, for mode, we have access, which is when the port behaves as a typical layer 2 switch port. We have network, which is when we instruct the port to behave as a layer 3 or routed port. And we also have this option of hybrid, where our physical port can act as both a switch port and a routed port at the same time. Just an ingenious concept. But for the sake of this particular module, we're just going to be configuring this as a run-of-the-mill access port. So mode access. And the CLI tells us that 115 must be shut down in order to make those changes. So we'll go ahead and shut that down. Go back into the Ethernet context. Change our mode to access. Now, when we change the mode to access, SROS does us a favor in that it automatically adjusts our MTU. So it knows that since and by default, the encapsulation type of an access port is null encapsulation. So it isn't expecting any VLAN tagged frames. It's just pretending that this switch port or this access port is connected directly to your PC or to a customer's router or to another switch. So those IP packets are going to be coming in at 1500 bytes, the router assumes. So since those packets are coming in at 1500 bytes, our operational MTU at layer 2 must be 1514 to account for those, our layer 2 header, our source and destination MAC and whatnot. However, when we specify our encapsulation type, again, we have .1Q, which is adding an extra 4 bits of header space to the MTU to account for our VLAN tag in our layer 2 frame. We have the null encapsulation, which is when we're instructing the switch port to not expect any VLAN tagged frames. We also have Q and Q, which is when we instruct the switch port to expect a VLAN stack. And this is where we'll have a outer VLAN, sometimes known as the transport VLAN, and an inner VLAN, sometimes known as the customer VLAN. Much like label stacking, which we'll get into later on when we cover LDP and MPLS. So by default, the encapsulation type is null, and we have our port configured with a 1514 MTU. So if we set the encapsulation to .1Q, and we issue the command show port module 1, we can see that SROS has automatically adjusted our MTU for us as well. So previously, when we had an encapsulation type of null, our MTU was 1514. Now that we've specified the encapsulation type of .1Q, SROS automatically adjusts our MTU to account for that 4-byte VLAN tag. And the same concept, if we specify an encapsulation type of Q and Q, if one VLAN tag is 4 bytes and we want the port to expect a stack of VLAN tags, then naturally we'd want the MTU to be increased by 8 bytes over the default as opposed to 4. So show port module 1, and we can see that our MTU is now 1522. So not only is it expecting a 4-byte outer VLAN tag, but it's also expecting a 4-byte inner VLAN tag as well. We aren't going to be doing any Q and Q tagging coming from the customer prim. So for the sake of our module, our encapsulation type is going to be .1Q. If we do show port module 1, we can see that our MTU is correct at 1518. So it's expecting a layer 2 frame at 1514 bytes plus the VLAN tag of 4 bytes. It is configured as an access port. However, it's still administratively down. Okay, this is our ports configuration 115. So all we'll do is issue a no shutdown, show port module 1, and this is what we'd like to see. We have our network facing ports with a jumbo MTU, all administratively up, and we have our access facing port or our customer facing port with an MTU of 1518 configured as an access port with .1Q encapsulation. So we'll go ahead and save this configuration. And if you've been following along in our last video, of course, we know that the command to save the configuration in SROS is admin save. However, this command by default must be issued from the root context. So just like we covered in our previous video, in order to issue a command from any context to any context, we can prepend that command with a /. So right now we're in port 115's configuration, and we see that by default, we can't issue that admin save command. However, if we prepend the admin save command with a /, we'll be able to save the configuration just fine. And of course, Control-Z puts us back in our root context. Now we'll go to N2 here, and we're going to configure the ports just in a few different ways. Again, SROS offers many different ways to skin the same cat. So just for the sake of example, we're going to incorporate our range command. So what we're going to do on N2, let's go back to our PowerPoint, is even though we're only going to be using 2 physical ports on N2, which is going to be port module 1, adapter 1, port 1, which faces N1, and module 1, adapter 1, port 2, which faces N3, we're going to go ahead and use our range command. So we're going to configure all of the network ports on N2 with the MTU of 9212, as stated in our goals. And of course, since N2, N3, N4, and N5 are going to be our P routers, getting into MPLS a little bit, they aren't going to have any customer-facing ports on them. We're not going to have any SAPs built within our core. All of the customer-aware information is going to remain at our provider edge, which in our topology is going to be N1 and N6. So on N2, just to show you how we don't have to skip through contexts to configure certain attributes or certain properties on whatever we're working on. From the root context, I can issue the command configure port module 1, adapter 1, and now we'll incorporate our range command. So we're going to say open bracket X, which in our case is going to be 1, through, which is 2 periods, Y, which in our case is going to be 5, then close brackets. So right now we're telling we're telling the service router that we want to configure ports on module 1, adapter 1, and physical ports 1 through 5. Open bracket 1, period 5, close bracket. SROS interprets that as ports 1 through 5. So this is our port range, or similar to an interface range on Junos. And since, of course, the ports are shut down by default, all we're going to be doing is configuring the MTU of 9212. And once we've got the MTU configured, we're going to use our range command again to bring all the ports into an operationally up status. So if we do show port module 1, we can see with 2 commands issued from the root context, we've reconfigured our MTU on all of our physical ports, as well as brought them into an administratively up state. And of course, to close the loop, we can issue an admin save. Now we're going to do the same thing for the rest of these service routers. N6 is going to be a little bit different because, again, on N6, we're going to have a SAP that's going to be configured for port 115. Or I should say port 115 is going to be configured for our SAP. So we're going to make that an access port. It's going to be customer facing. So we're going to use the commands window here. And again, I'm logged into, let's see, N3 and 4 and 5 and N6. And I'm just going to configure all the ports, ports 1 through 5 in the same fashion as I did on N2. But once we get to N6, we're going to reconfigure port 115 as our access port rather than a network port. So into the command window goes the exact same commands I issued on N1, which was configure port module 1, adapter 1, open bracket, our start, which is port 1, through our stop, which is port 5, Ethernet MTU 9212, and we're going to rinse and repeat that. Configure port module 1, adapter 1, ports 1 through 5, no shutdown. We can do show port module 1. And we see that on N3, on N4, on N5, and on N6. All of our ports are configured as network ports with null encapsulation, along with an MTU of 9212. So port 6 is going to be a little bit different. And we'll just take a look at the port configuration here. Admin display config, match port, context all. And this is the guy that we're concerned about, because this is going to be our the port for our service access point. It's going to be customer facing, and it's also going to face a switch that we're going to throw into our topology for the sake of trunking. So first, let's enter that individual port's context. Now, what's going to happen when we try to change this from a network port, which it is by default, into an access port? Of course, it's going to deny us because the port is not shut down. So again, in order to make any changes to a physical port in SRS, the port must be shut down. So as you can see now, the port is shut down. So at this point, we can change the, first we could actually remove that MTU. All right, just to default the port, so to speak. So now at this point, we can change the Ethernet mode to access. And we can also change the Ethernet encapsulation type to .1Q. Because again, this is our customer-facing interface. So we want this switch port to expect VLAN tagged frames, because each of our customers, each of their services, they're going to be segregated by VLAN tag. So if you do show port module 1, you can see that on N6, ports 1 through 4 are configured as network ports with the null encapsulation type and that MTU of 9212, as well as being internet administratively upstate. And 115 It's configured as an access port. That's what we wanted. It's configured with an MTU of 1518, again, which is accounting for the 4 bytes of extra space we will need for our VLAN tag, so that's correct. However, it's still in an administratively down state. So if you take a look at the port's configuration by entering the command info, we can see that sure enough, the port is shut down. So we're just going to issue a no shutdown command. Take a look at the configuration. It is shut down or no longer shut down. So when we enter the command show port module 1, all of our ports are administratively up. All of our network facing ports or our core facing network ports have our jumbo MTU, and our lonely customer facing access port has our MTU for VLAN encapsulation. So at this point, we're just going to issue a /admin save. And again, that's because I don't know which context. For example, this guy might be in the configure system context. This guy might be in the configure port 112 context. This guy might be in the configure port 113 context. And this guy is just going to be en route. So again, by prepending this command with a /admin save, SROS will accept the command regardless of the context that you're currently in. So we've got our configuration saved on all of our service routers. All right. So we've configured all of our physical ports, all of the core-facing network ports with an MTU of 9212. We've configured both of our switch ports, 115 on N1 and N6 as access ports with .1Q encapsulation. And we've also configured each physical port to be administratively up. So our next step is to configure each service router's system interface with the appropriate IP address. So like I said before, our system address, and we could do the command show router interface. And we have our system address. So our system address is going to be our synonymous with our loopback 0 address, if you were used to working on Cisco's, or our LO0 unit 0 address, if you're used to working on Junipers. But the core concept remains the same in that this is the address of the system itself. So this is where our peerings are going to occur, because we're going to assume that if we're in a service router environment, and we're in a market that's above like a tier 5 or a tier 6 market, okay, we're going to have more than one path in and out of that market, or a given router should have more than one path, outside of its local POP, I should say, or colo. So we're going to peer our protocols with each router's system address, because like I said previously, if we have multiple ways in and out of a given router, we wouldn't want to peer with one particular link address, or 1/30, or in our case a /28, because if that physical address goes down, well, then we lose our protocol peering. However, if we have redundancy in place, then when we've peered with our system address, when that link goes down, that protocol won't go down, given, let's say, for example, ISIS, the default timeout on ISIS is 27 seconds. So that protocol, even if the link goes down, our link state protocol, or ISIS, will issue a link state update and flood all of its neighbors with that link state update, letting its neighbors know that this particular link is down. However, that peering will remain. The system address will still be reachable. So the overlying protocols that depend on our IGP, for example, LDP, RSVP traffic engineering, BGP, those protocols are going to remain operationally up because they have more than one way to reach a particular router's system address. So looking at the system interface here, our logical router interface system, we could see that, by default, each SR comes with a system interface configured. It knows that eventually you're going to want to uniquely address this intermediate system. So we could take a look at the details of our logical router interface system. We could see it's administratively up by default, as any good loopback address should be, but it's operationally down. So let's take a look at the detail. Show router interface system detail. And right off the bat, this field, the down region code, it's telling us why this interface is operationally down. And in our particular case, it's because we have no interface address configured. And this particular, and we have a ton of fields, as you can see on these interfaces within SROS, a ton of billing, our QoS, our route filtering. And as we just carrying over from the first video, some of the properties or some of the things that a device needs to be capable of in order to be designated as a service router, QoS, filtering, billing, residential service delivery, business service delivery, mobile core and backhaul, etc. So we're seeing a little bit of those capabilities here. And again, our filtering, our accounting or billing, and our QoS. All right, so scrolling back up here, we see that the down region code is because we have no interface address configured. Now, the down region code is synonymous with another field, which I absolutely love on Service Router OS, which is the flags field. And the flags field is, again, just another field like down region code that tells us exactly why our service or our protocol, or in this case, our logical router interface, isn't in an operationally up state. So it'll tell us everything we need to know. For example, it'll tell us we're not receiving an ingress virtual circuit label. We aren't receiving an egress virtual circuit label. The SDP, or the service distribution point, is operationally down. The physical port is administratively down. So the flags field makes it very, very, very simple for a network operator to zero in on an exact root cause of a given issue. So since the root cause of our given issue is that no interface is configured, or I should say no interface address is configured, we'll go ahead and take care of that. So we're going to enter the configure context, all right? And since this is a logical router interface, we're going to enter the router context and specify interface system. So this is our logical router interface system configuration so far. It's only no shutdown. Okay. So in order to specify a logical address, now let me push the tab key so you can see all of the options that you have available. If for some reason you want to run BFD on your system address, you have the option. You can run DHCP as well. And by default, SROS knows that the system address is a loopback interface. But if we wanted to create or emulate networks on this router, we can do so by specifying the loopback property under our router interface attributes. So in our example, and again, we can see our QoS options here as well, but in our example, the only thing we're going to be concerned with is our address. So our definition is this command assigns an IP address, IP subnet, broadcast address format to the interface. So let's go back to our PowerPoint. And our system address for N1 is going to be 1.1.1.1/32. So we're just going to say address 1.1.1.1/32. So one of the good things about SROS, much like the next generation, I call them next generation, but they're kind of old now. At one point in time, operating systems that would run on devices didn't accept CIDR notation or classless interdomain routing notation. This meant that you had to be very, very prevalent in subnet calculations, and its greatest achievement is serving as a awesome point of failure when it comes to a circuit not being able to establish itself operational wise, a subnet mask mismatch, so to speak. So by having the ability to enter things with CIDR notation, not only does it keep everything sort of more in line with the concept of prefixes, as opposed to separating things into sort of an idea of this is the IP address, and then you have this entirely separate thing called the subnet mask, which is 32 bits long, etc. It allows you to interpret things and allows you to issue commands so that the OS can interpret things based on prefixes. And once we get into things like BGP, our subnet masks, they aren't going to go completely out the door, but we're going to be dealing with prefixes as opposed to just a IP address, and a subnet mask. So we've entered the address 1.1.1.1. And again, we're under our system router interface. And if we issue the back command again, right now we're in our config router context. So if we issue our info command here, we can see that under our logical router interface system, we have our address configured. So we can do a show router interface system. And we can see it's now operationally up. And if we specify detail, you can see that our previous field, which was, let's see, down region code, that's no longer there. So we've done our part. The system address is now operationally up because we assigned it an interface address. So let's go back to our PowerPoint presentation. And at this point, we have our logical router interface system configured correctly. So now we're going to configure our logical router interface 2N2 that's going to connect N1 directly to N2. So since we're already in the configure router context, we're going to specify our interface name 2N2. Let's I'll let you see some of the options that we have here. But again, we're just going to specify the interface name 2N2. That's going to be our logical router interface. Now, the first thing I typically like to do is bind my physical port to my logical router interface so I don't forget. So the command to do that is going to be port. And then we just specify the physical port we'd like bound to this logical router interface. In our case, it's going to be physical port module 1, adapter 1, port 1, or 111. By typing the info command, we could look at the running configuration. And we can see currently within our logical router interface 2N2, we've bound the physical port 111 to it, and we have it in an operationally, I should say, an administratively up state at this point. So the last step that we're going to do is configure our logical IP address, which is going to be 10.1.2.1/28. And the way we do that with our logical router interface 2N2 is the same way we did it with our logical router interface system. We simply type address 10.1.2.1/28. So this is the configuration for our logical router interface to N2. That's going to be directly connected to N2. If you go back into the router context, we can see the configuration for both of our logical router interfaces. Logical router interface system has an address of 1.1.1.1/32. That's what we want. Logical router interface 2N2 has an address of 10.1.2.1/28 and a physical port binding of 111. Logical router interface 2N2 has an address of 10.1.2.1/28 and a physical port binding of 1/1/1. So that's exactly what we want. Holding Control and pressing Z will put us back in the root context. And if we issue the command show router interface, we can see that both of our router interfaces do show up now with their specified IP addresses. And it also lets us know which port that a given, which physical port that a given logical router interface is bound to. And just for the sake of argument, we'll ping across our link. And of course, this request is timing out because we haven't configured the other side. But if we want to ping locally, you can see that our packets do come back. All right, now let's just do a show system license. See how much time we got. We got 20 minutes. Okay. And the reason I have to do this periodically is because these images are strictly for educational use only. So if you enjoy the concept of the service router operating system, please purchase the legitimate images from Nokia. But since these are unlicensed, again, for educational purposes only, they reboot once each hour, which I don't really see as a bad thing. It's actually a very great way to improve your speed and improve your troubleshooting. Because if you want to take a given network from 0 to, multi-protocol BGP within an hour, this built-in mechanism makes that very, very, very easy to do, easy to work with the time constraints. So at this point, let's take a look at our running configuration. This is what I wanted. So at this point, let's take a look at our goals. Configure each service router system interface with the appropriate IP address. We've done that for N1. We're going to continue that for the other service routers and configure the other logical router interfaces with their appropriate IP addresses. Again, we've done that for N1, the interface 2N2, and we're going to do that for the other ones as well. So let's work on N2. And again, we're not going to take too much time to do this. If you'd like more detail, you could rewind slightly and see how I step through N1's configuration. So the first thing we'll do on these is we'll just configure each router system address. So configure system. It's a logical router interface. Configure router interface system. address. I want to just copy this. And since we're on N2, our system address is going to be 2.2.2.2/32. Likewise for N3, our system address is going to be 3.3.3.3/32. For N4, now we're not in the root context, so we're just going to prepend this again with a /. And since we're in the physical port context, which one I'm not sure, it looks like physical port 112's context, issuing this / in front of our command allows us to configure or send commands to different contexts and get information from different contexts, regardless of the context that we're currently in. So for N4, our system address is going to be 4.4.4.4/32. For N5, it's going to be 5.5.5.5/32. And we see the importance of prepending our commands. If we aren't in the correct context, here we can see the importance of prepending our commands with a /. Now, not to get too much off topic here, but say, for example, we had a script where we had a method of procedure that would configure a subset of ports and then bind those ports to router interfaces and then configure services for those router interfaces and bind those services to SAPs built off of a specific port. If we prepended, well, let's take it the old-fashioned way. If we weren't to use this sort of flat configuration, we would have to go in context by context, not only make sure that we're in the correct context, but make sure that we issue the correct command within the correct context. But then once we've done that, we have to make sure that we've backed our way out of whatever context that we're in. So for example, the system context, there are only certain commands that you can issue within the system context. Okay, the same applies if we were in a physical port context. There are only certain commands that you can issue within that particular context. And just going back to our system context here. However, if you prepend your commands with a /, then that allows you, again, to issue commands into that context, regardless of the context that you're currently in. And let's just do it here again, just so that we can see. Again, I'm issuing a configure router interface system address 6.6.6.6/32 for N6, and it's telling us the command is bad, which it is. But to make it a good command, we simply prepend it with the /. All right. Now let's do / show router interface. And let's just make sure that our system addresses on each router are correct. So for N6, we have a system address of all 6s/32. N5, all 5/32. N4, all 4s/32. N3, all 3s/32. And of course, N1 and N2, we've accomplished those already. So we're just going to issue a / admin save to all of our sessions. That'll save our running configuration. Let's see how much time we have. Show system license, more than enough time. All right, so at this point, we've got all of our system interfaces, our router logical interfaces called system. Those are all configured properly. So the last thing we'll do is we'll go ahead and not only establish the physical connections between these routers, but we'll also configure those physical connections as well. And that's something I forgot to do. So going back to GNS3, we're just going to mimic this topology. So we can see physical port 111 on N1. goes to physical port 111 on N2. Physical port 112 on N2 goes to physical port 111 on N3, so on and so forth. So we're just gonna roll through this. 112 on N2 goes to 111 on N3. 112 on N3 goes to 111 on N4. 112 on N4 goes to 112 on N5. And 111 on N5, of course, goes to 111 on N6. So at this point, we have our physical links established. Our routers are physically connected the way we'd like them to be. All right, so once we've got them physically connected, we're going to go ahead and configure our logical router interfaces. And again, we aren't going to spend too much time on this. If you want a more in-depth approach, simply rewind the video to the work we did on router N1. So on N2, we're going to enter the configure router context. And we can see all we have here is our system address or a logical router interface system. So first thing we're going to do is we're going to configure our logical router interface to N1 that's going to be facing the router N1. So we're going to take care of this guy right here. It's going to have an IP address of 10.1.2.2/28, and the physical port binding is going to be 1/1/1. So we specify interface to N1, port 111, address 10.1.2.2/28. Let's go back. And just like that, we have our our logical router interface to N1 built on N2. So if we go back here, where are those ping commands that we issued earlier? Here they go. So earlier, we tried to ping this .2 host from N1, but our request was timing out for two reasons. One, we didn't have a physical connection to the router N2. Three, we didn't have a logical router interface representing that physical connection from N1 to N2. And also, we didn't have a physical port bound to that logical router interface. So we're just going to take this same ping command and paste it. And as you can see now, N2 is responding. And we can check out our ARP table with show router, ARP. And again, we have the IP address of our local interfaces, our system address, and our logical router interface to N2. But we also have an ARP entry for our logical router interface to N1 that's built on N2. And just for the sake of nullius in verba, we could take this MAC address that ends in echo echo 01 and go over to N2. And since we know that our physical port 111 is what's facing N1, then on N2, port 111's MAC address should end in the same echo echo 01. So we're just going to do show port 111 detail, and we'll scroll through this information looking for our hardware address, which we have right here, echo echo 01. So as you can see, this is the actual ARP from our, or even conveniently has our logical router interface as well, but this is a dynamic entry that's coming over this physical port with that logical address. All right. So if we do a show router interfaces or interface, you can see we have our system, our logical router interface system, and our logical router interface 2 in 1 configured. And let's just do a show system license See how much time we got. 10 minutes. All right. So our next step for N2 is going to be to configure our logical router interface, excuse me, to N3 with a logical IP address of 10.2.3.2/28 and a physical port binding of 112. So we're just going to specify interface to N3, port 112, address 10.2.3.2/28. And if we go back into our configure router context and look at the info, you can see we have our logical router interface system with an address of all twos, which we've taken care of. We have our logical router interface to N1, which is 10.1.2.2/28, physically bound to port 111. Our logical router interface to N1, logical address 10.1.2.2/28, physical port binding 1/1/1, and likewise with our interface to N3 with the logical address, I'm sorry, of 10.2.3.2/28 and a physical port binding of 112. Now we're going to rinse and repeat that for N3, N4, N5, and N6. And we'll save everything at the end, but I'm just going to sort of blow through this. But if you are curious, you can rewind the video and it'll go into better detail. Configure router, interface to N2. Our port's going to be 111. And our address is going to be 10.2.3.3/28. You're going to go back into our router context. We're going to specify the interface to N4. Our port's going to be 112. Our address is going to be 10.3.4.3/28. All right, now on to N4. Right now we're in the context of the physical port 112. So we're just going to enter our configure router context. So we're just going to issue the command / configure router interface. First, let's take a look at the running configuration. All right, interface to N3. Physical port binding is going to be 111. Our address is going to be 10.3.4.4/28. Going to specify the interface to N5. Our physical port binding is going to be 112, and our address is going to be 10.4.5.4/28. All right. So just to double check, 112 on N4 is going to connect to 112 on N5. So let's move over to N5. And again, we're in the configure system context. Let's just move over into configure router. Take a look at our configuration. I'm going to specify the logical router interface to N4. That port binding, again, is going to be 112. Our address is going to be 10.4.5.5/28. And let's create the interface for N6. And this physical port is going to be 111. Address 10.5.6.5/28. All right. And lastly, we've got N6. So this time I'm just going to hold Control and press Z to get back into the root context. I'll configure this logical interface from the root context. So we're just going to do configure router interface to N5, port 111. Configure router interface to N5, address 10.5.6.6/28. Now let's hurry up and admin save these before our routers reboot on us. But from here, we can just pretty much start pinging the other sides of our interfaces. So from N1, we could ping N2's directly connected interface. And from N2, hold Control and pressing Z will put me back in the root context. Show router interface. We're just going to ping N3's directly connected interface, 10.2.3.3. And we see those responses come back. From N3, so router interface, we're going to ping N4's directly connected interface, which is 10.3.4.4. Those come back. From N4, show router interface, we're going to ping N5, which is 10.4.5.5. Those come back. And from N5, show router interface, we're going to ping N6. And those come back as well. So at this point, we've accomplished all of our goals and the router's perfect. We barely made it. They're starting to reboot. So at this point, we've accomplished all of our goals. We've configured all of our physical ports the way that they're supposed to be configured, with our core or network-facing ports having a high MTU of 9212, and our customer or access ports having an MTU appropriate with .1Q encapsulation, as well as being configured as access ports. Each of our physical ports are administratively up. We have configured each service router's system interface with the appropriate IP address. Again, N1 is going to be all 1/32, N2 all 2/32, all the way up to N6 being all 6s with a /32 on the end. We've also configured the other logical router interfaces with their appropriate IP addresses. So not only did we configure them, we configured our physical port bindings. We've configured our logical IP addresses. We've even took a look at our MAC address on our physical ports, and we've pinged each directly connected interface. So I'm just going to give SROS a little bit time to boot here. Oh, N2 didn't take any time, did it? So let's log into N2 here. And our next module, since we've sort of gone through the process of first configuring the hardware of our Nokia devices, followed by configuring the actual system name on our Nokia devices, followed by our ports, as well as our logical router interfaces. And actually, this looks a little bit incorrect here. I mean, this MTU won't hurt having a bigger than usual MTU, but N6, I believe, is correct in that it has a MTU of 1518. Yeah, so for the sake of congruity, we'll reconfigure this physical port 115. So we're going to first shut the port down, configure port 115, and take a look at the configuration here. And we're just going to remove this MTU. So we're going to say Ethernet, no MTU, or again, we can go into the Ethernet context and specify no MTU. Again, they both accomplish the same thing. And let's do a show port module 1. And that's the MTU we were looking for. So we'll bring this port back up. Show port module 1. Good to go. Control Z brings me back to the root context. So like I was saying, so we've configured our hardware. We've configured our hardware's here. We've configured our system name. We've configured all of our ports. We've configured our logical router interfaces, not just the system interface, but also all of our network interfaces as well. And on N1, as well as N6, we've configured port 115 as an access port with .1Q encapsulation, because this is the port that's going to face our switch. And we're going to segment our subscriber services based on their VLANs. So we aren't doing any type of Q and Q encapsulation. We aren't stacking VLANs, but we need the port to be able to recognize a certain VLAN when that frame ingresses our SAP. So our next module is going to cover establishing dynamic routing, because as it stands, all these routers can reach each other as long as they're directly connected. So for example, router N6, given our topology, in a perfect world would be able to reach router N1, since these are both our provider edge routers. We could say that our subscriber has a customer site in Los Angeles stub to this provider edge, and our subscriber has another site in New York that's stubbed to this provider edge in 6. So in order for those in order for that service, whatever service that customer wants, whether it's a virtual private wire service like an ePipe or an iPipe, or it's a VPLS where the service provider emulates a virtual switch, or virtual private routed network, or VPRN, where the service provider emulates a virtual router, or even an IES, an Internet Enhanced Service, which provides sort of like a direct termination. Well, it provides a direct connection for the subscriber to the internet. And not only does it provide that direct connection, you can also apply QoS, you can apply billing, and you can apply route filtering at that customer-facing SAP. So what it is, in a nutshell, the IES, or Internet Enhanced Service, it's a service that's configured as a SAP. Okay, it's a subscriber's service that's configured as a SAP that offers a direct connection to the internet through the given service provider. So our next module is going to cover dynamic routing. We're going to use intermediate system to intermediate system in order to establish dynamic routing. So for example, when we try to ping from N6 to N1, we get the message no route to destination, which is absolutely true. If we look in router N6's route table, which is show router route table, all we have are our directly connected routes, or our local routes. Depending on what you're looking at, SROS may refer to these routes sometimes as local. Sometimes, like for example, if you're configuring a policy statement or a routing policy, then SROS refers to these local routes as direct routes. But they both mean the same thing. Local, direct, directly connected, they're all the same thing. So in router N6's routing table, or the routing information base, we see that it really doesn't have a route to N1, okay? And even if we look at the forwarding information base, which was show router, is it fib1, I believe? Yep. Even in our forwarding information base, we don't have a route to N1. As a matter of fact, we don't have a route beyond our directly connected peer, which is N5. So even if we wanted to ping, for example, from N6, even if it's directly connected to N5, and we wanted to ping the interface that connects N5 to N4, which in our example is 10.4.5.5/28, we still wouldn't be able to do it. Now, this route is on the same device as 10.5.6.5. yet there's no dynamic learning or dynamic exchange occurring between N6 and N5. So N5 isn't telling N6 about its direct connection to N4 because that's just not what we're instructing the router to do. Right now, we've just said, here's a local interface or here's a local Ethernet segment, and that's it. So in our next video, what we're going to do is we're going to establish dynamic routing so that not only will N6 know about N4's connection or N5's connection to N4, but N6 is going to learn all of these connections as well as all of these system addresses. So eventually, we'll have a route in our forwarding information base for router N1's system address. And that route is going to reach N6 through our dynamic link state protocol, which in our case is going to be intermediate system to intermediate system. And once we have that established, then like we touched on earlier, we can start peering our protocols based on those system addresses. So at this point, I believe we are through. Again, I appreciate you checking out the presentation. Feedback is always appreciated. If there was misinformation anywhere, please let me know. If I misspoke, let me know. If there's anything I could do to improve, please let me know. I enjoy making these videos. So of course I want to get them as accurate and as truthful as possible. So until next time, you guys have a good one.